So as we have discussed in the previous lecture, the classification of second order partial differential equation, which we have seen certain examples which we have converted in, that is into its canonical form of this semi-linear partial differential equation of second order. Today we will discuss regarding the solution of one-dimensional wave equation, and in that we are considering the very special case for that. It is a vibration for infinite string. So what is the problem? First of all, let us understand that we have given one infinite string and we'll make some force into it, and we need to find out what will be the position of any point at time t and at the position x. So here y is a displacement variable which is depends on x and y. X is gives your position and t will gives your time. So here the situation is there is an infinite string is given to us, and we'll make some moment, or we can give some extra force to this infinite string. And what will happen at x position? So here it is x is 0. So what will happen at this point x, and what will happen at time t? The vertical distance is nothing but the y. That means the displacement. How much displacement will occur? So that is the one-dimensional wave equation is there. And for that wave equation, we already have one video is prepared for that. You can go and see that the one-dimensional wave equation is considered like this. So the first objective is to convert this one-dimensional wave equation into the canonical form. So as we have discussed in my previous video, that if you want to convert into the canonical form, then first of all you have to compare this with this semi-linear equation. That is, here instead of u we have y. So comparing with ryy plus syt plus tt plus some function of f of xy, sorry, xt, y, yx and yt equal to 0. If you compare with this, we obtain r is equal to, the value of r we know it is 1, s is 0, and the value of t will be minus 1 upon c square. So now we need to see what will be the s square minus 4 rt. So s is 0 minus 4, r is 1, t is 1 upon c square, so that will be gives me 4 by c square, which is always positive. Since this value is always positive, the given equation is hyperbolic type. That means this is a wave equation, and we have seen that the wave equation is an example of hyperbolic type equation. So that's why we can say that this equation 1, if I can call it, this is equation 1. So this will be the equation 1, is the wave equation. So the equation 1 is hyperbolic type. Now, to find out the canonical form of that wave equation, consider the quadratic polynomial, that is r alpha square plus s alpha plus t equal to 0. That will gives me alpha square plus 0 into alpha, because r is 1, s is 0, minus 1 upon c square. That is the value of t equal to 0. So therefore, this will gives me alpha is equal to plus or minus c for some constant c. Okay. So we have alpha is plus or minus 1 by c. We'll take lambda is equal to 1 by c and lambda 2 is equal to 1 minus 1 by c. So now consider dt by dx instead of dy by dx, we'll consider dt by dx. Plus lambda 1 is equal to 0 and dt by dx plus lambda 2 equal to 0. So that's why this will gives you dt by dx plus lambda 1, that is 1 by c, equal to 0, and this will give you dt by dx plus minus 1 by c is equal to 0. So therefore, if I simplify this by separable variable method, this will gives me c into t plus x is equal to constant. Let's say that constant is c1, and we'll have c minus x is equal to c2. That is another constant we have. That means by separable variable method, if I can solve this two ordinary differential equation, we'll have this. Now, these two equations are actually known as the characteristic curve of equation 1. I can say that c minus x is equal to constant c2 and x plus c2 is equal to c1 are the characteristic curves of equation 1. Now consider xi equal to x minus ct and eta is equal to x plus ct. These are the two variables we have. This c2 is I can consider as minus c2, no problem with the constant by adjusting this minus sign. So we'll consider xi and eta as this. So now we'll to change our differential equation, that is y xx is equal to 1 by c square ytt into this xi and eta. So y is a function of xi and eta, and xi and eta are the functions of x and t. That's why we have it is y x will be xi, y xi into xi x plus y eta into eta x. Y xi as it is, xi x, we just see that from this xi x is 1 and xi t is minus c. Eta x is 1 and eta t is c. So this will be 1 plus y eta because eta x is also 1. So y t will gives me y eta t plus y xi t plus y eta t, which will gives me c is common out. In bracket yt is minus, so it is minus xi plus y eta. Now yxx we have to calculate. That is the derivative of this one. Y xi into xi x plus y xi eta into eta x plus for yt, that is y eta xi x plus y eta x. But xi x and eta x is 1. So that's why it will give me xi plus 2 times y xi eta plus y eta eta. Now y tt we need to calculate. That is the derivative of this quantity. Since this c is constant, so that's take out. Now minus y xi derivative of that with respect to t will give me minus y xi t minus y xi eta eta t plus y eta xi t plus y eta 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 t. But as we know that xi t is minus, so this will give me minus minus plus, and this is also gives me minus minus plus. So this will gives me minus sign. So that's 4. The ytt is c square into, because now every time it will c come up. So it is yt, it is minus, so it is minus y xi is minus sign. Eta t is c, so that's why it is c, and this together, this quantity and this quantity combined, that will gives me minus 2 times xi eta plus y eta eta. So the quantity you will left is this. Now we'll substitute this value into y xx is equal to 1 by c square ytt. This is given to us. So that's why it is y xx will have this y xi plus 2 times y xi eta plus y eta eta. So that is y xi plus 2 times y eta xi plus y eta eta. That is, this c square will cancel out, and here we will have y xi minus 2y xi eta plus y eta eta. So finally the quantity is left is 4 times y xi eta is equal to 0. That will implies y xi eta is 0, because this y xi is cancelled out with this one, because the c square will get cancelled, and this quantity is cancelled with this one, this quantity is cancelled with this one. So only the quantity is left is this. So this is the canonical form of the equation which is of hyperbolic type, that is y xi eta is equal to this thing. So now we'll have the y xi eta. So ultimate question is to what will be the solution for this one-dimensional wave equation. So we'll have this is the canonical form. So if I integrate this with respect to eta, so integrating with respect to eta, keeping xi constant, we get del y by del xi is equal to, because we are integrating with respect to eta, so one will go on and it will have a function. Let's say that function is f of xi, because xi is we have kept as a constant, so that constant is maybe a function of xi, where f is arbitrary function. Now again integrating with respect to xi, keeping eta constant, we'll have y is equal to integration of f of xi d xi plus some constant g of eta. because that constant may be a function of eta. Okay, where f is arbitrary function. Sorry, g is arbitrary function. I will consider this entire integration. Maybe some some integration will be there. I will call it this is as f dash, or I can say it is f1. If I can say this is f1, then the final answer will have y is equal to f of xi plus g of eta, where we'll consider this f1 is equal to f1 of xi will be integration of f of y dz. So that is of some function will be there. Sorry, here it is f1 and here it is f. So we'll consider this f is a function which is integration of this. Where this f, here this f, capital F and capital G, both of them are 2 times differentiable function, and which is known as, and it's contained 2 arbitrary functions. That's why the solution which we have occur here, it is a regular solution for the equation 1. So therefore, what is a y of xt will got, it is f of, what will be the value of xi? The value of the xi which we have is this x minus xt, eta is x plus xt. So that's why we can substitute that value here. That is x minus ct plus g is equal to x plus ct is the regular solution of the equation yxx is equal to 1 by c square ytt if we consider, if we consider capital F and capital G belongs to C2. The C2 is the set of all 2 times differentiable function. So that's why it is called the regular solution. And we'll consider now some initial condition for this wave equation. That means initially we know that the position may be at some place. That means at time t equal to 0, it may happen that the string is some position, and at time t equal to 0, the velocity will be some function. That means some velocity is already there in the string. So we are considering 2 initial conditions here. So let the initial condition be given as follows. That is y of x0 is equal to f of x. That is at time t equal to 0. The displacement of the string is f of x. Some function it will be there. And yt at x0. That means at time t is equal to 0, the velocity will be g of x. This will gives me velocity. This is gives me the displacement at time t equal to 0. This is the initial condition where your value of x is between 0 to infinity. So where I can say that where y is equal to f of x is the initial position of the string. So this is a small fx which will be different from the capital Fx. So please keep this in mind. And g of x is the initial velocity at the point x. So you have a string which having some initial velocity is already there, and we are in that initial velocity we are putting some effort, or we can put some. So to do this one, we need to calculate what will be this function capital F and capital G. That will gives me the general solution. Okay, so to find out that, we have y of xt is this. So we have y of xt will be capital F of x minus ct plus capital G of x plus ct. Putting t equal to 0, we get y of x0 is equal to capital F of x because t is 0, and this will gives me g of f of x because t is 0. But what is y of x0? At time t equal to 0, we have considered y of x0 is f of x. So therefore, we'll have capital F of x plus capital G of x is equal to small f of x. Now, if I differentiate y of xt with respect to t, differentiating y of xt with respect to t, we get, so we'll get yt of x comma t. That means the derivative of this function, that is actually what is the situation is this f is a function of some variable s, where s is nothing but the x minus ct, and this s is a variable, two variable function x and t. So the derivative of f with respect to x or t will have this. That means f dash of x minus ct, and the derivative of x minus ct will gives me minus c, plus g dash of x minus ct, and the derivative of x plus ct, and the derivative of x plus ct will gives me c. So therefore, what we have, by putting t equal to 0 here, t equal to 0, we obtain y of x0, yt of yt at x0 will be, you just substitute t equal to 0 here, that will gives me minus c f dash of x, it will minus c f dash of x plus c into g dash of x, because this is the value of c, that is g dash of x, and that is equal to, we have considered small g of x is equal to minus c into f dash of x plus c into g dash of x. Solve these two equations. Let's say this is equation number 2 and this is equation number 1. So 3. Solving equation 2 and 3. So how to solve this equation 2 and 3? So if I integrate this equation 3 with respect to x, so before I just write down the solving equation 2 and 3, I will say it is, we need to solve equation 2 and 3. and we need to calculate what is the capital F and what is capital G, because they are arbitrary functions. This small fx and small gx are given to us. So with that note, we integrate equation 3 with respect to x. We get integration of g of x in the interval x0 to x. So it is in the interval x0 to x. We are integrating in this interval dx. That is integration of f dash of x by fundamental theorem of calculus will gives me f of x, that is minus c f of x plus c g of x. Now we'll call this as equation number 4. We have already equation 2, which is fx plus gx is small fx. So we'll have fx plus gx is equal to small fx. If I multiply by c this equation, then this will give me, this will get cancelled out. And if I add them, we'll have here on this side, we'll have x0 to x g of x plus c times f of x is equal to c times 2 times c g of x. That means the value of g we get from this, it is 1 by 2c c into fx plus integration x0 to x g of x dx. And if I subtract this two, this will we got by adding the value, this equation, this two equation. If I subtract this two equation, then we'll get fx, and the value of fx we obtain is capital Fx is 1 by 2c into c times fx minus x0 to x fx dx. And therefore, by the solution of equation 1 will be y of xt will be 1 by 2, because the fx value is this, c will get cancelled out. If I add this two value, that means this is fx and this is gx. This is the value of f and g we get. Our solution is capital F of x minus ct plus g of x plus ct. So I substitute this value of f here, that will give me 1 by 2 small fx minus ct minus integration x0 to c 1 by 2c g of x dx plus the g of x plus ct, but instead of x we have, it is x minus ct. Instead of x we have, whenever x we have, it is x minus ct. And for g it is 1 by 2 f of x, but f of x is x plus ct here, plus 1 by 2c integration x0 to x minus ct g of x dx. So the finally what you got is y of xt is 1 by 2 f of x minus ct plus f of x plus ct plus 1 by 2c. Since this minus sign, I will interchange this limit, that will become plus, and we'll have it is c minus, sorry, x minus ct to x0 g of x dx plus x0 to c plus ct g of x dx. And if I take this two integration combined, because it is starting from x minus ct to x0 and x0 to c plus ct, so finally we'll have it is this is the solution for one-dimensional wave equation for infinite string x minus ct to x plus ct g of x dx. And this solution has a name, and it's the name of this solution is called D'Alembert solution. This solution is known as D'Alembert solution. And we required this f and g, and this f and g should be is 2 times differentiable function and g is 1 time differentiable function. So this f is 2 times differentiable function, and that we are looking for. So ultimately what we have discussed here, we have discussed the solution for vibrating string if the initial conditions are given, that is y of x0 is equal to f of x and yt at x0 is equal to g of x. For example, if I can ask you, example, find the solution of wave equation y xx is equal to 1 by 4 ytt with the condition that x is between minus infinity to plus infinity and t is greater than 0, with initial condition that y of x comma 0 is x. That means initially the displacement is x, and yt at x0 is, let's say it is 0 if your x is between minus infinity to infinity. So here if you just compare the previous case which we have discussed here, where your y is satisfying the wave equation. So we know that the D'Alembert solution of the initial value problem yxx is equal to 1 by c square ytt with x is between this, with y of x0 is small fx and yt at x0 is small gx for every value which is in between, is the D'Alembert solution is, with this situation, is y of xt, it is equal to 1 by 2 f of x minus ct plus g of x plus ct, sorry, f of x plus ct plus 1 by 2c integration x minus ct to x plus ct g of x dx. This is the solution. Here, let us see what is given. What is the value of c? That is 1 by 4 is here. So instead of 1 by c square, we have 1 by 4. So the value of c is 2. Small fx in this situation, it is given x. Okay, because that is a displacement. So small fx is x. And small gx is 0. So therefore, the solution of the given equation is y of xt will be 1 by 2. F of f is this, that is x. So x minus c is 2. So x minus 2t plus x plus 2t. And this g function is 0. So this integration will be 0. So this term will not be there, and if you simplify this, you will have x. So that means if your initial position is x, then at every time it will stay as at x. I will give you one problem as a homework. You can try for this problem. Find the solution of ytt is equal to 1 by 9 ytt. Sorry, yxx is equal to 1 by 9 ytt. If your value of x is between minus infinity to infinity, t is greater than 0, with initial condition, that means at time t equal to 0, let us consider the velocity, the displacement is x square if your value of x is between minus infinity to plus infinity, and that velocity will be at time t equal to 0 will be, let's say, x if it is between minus infinity to infinity. Your x is between minus infinity to infinity. So that's it for this today's lecture. Try to solve this problem as your own. What is the given situation is you have, and according to work out. If you have any question, you can ask.